Flexible metal conduit and liquid-tight flexible metal conduit are not listed as grounding paths according to the National Electrical Code. An external equipment grounding conductor must be installed with both types of flexible conduit. Installing fittings with a grounding lug on each end of the flexible conduit and an external bonding jumper around the conduit is a recommended practice for enhancing grounding and reducing the risk of electrical shock. This method provides a positive electrical connection between the flexible conduit and the grounding system, ensuring a low impedance path for fault currents. The cost of installing grounding lug fittings and an external bonding jumper is relatively low. The added cost is offset by the increased safety and reliability of the installation. The generator output conduits carry high currents, so proper grounding is crucial for fault protection and personnel safety. The grounding lug fittings create a low-resistance connection that limits the voltage rise in the flexible conduit in the event of a ground fault. The external bonding jumper provides a redundant grounding path, reducing the risk of a floating ground condition. Based on the National Electrical Code requirements and the electrical considerations, it is highly recommended to install grounding lug fittings with an external bonding jumper on each end of the flexible conduit when connecting to a generator set. This practice enhances grounding and increases the safety and reliability of the installation. When dealing with electrical systems, especially those involving generators, safety and reliability are paramount. The National Electrical Code, commonly referred to as the NEC, provides a comprehensive set of standards and guidelines to ensure these critical aspects are met. One key area of focus is grounding, which plays a vital role in protecting both equipment and personnel from electrical hazards. When connecting conduits to a generator set, it is common practice to use short lengths of flexible metal conduit or liquid-type flexible metal conduit to accommodate vibration. However, these flexible conduits are not recognized by the NEC as suitable grounding paths. Therefore, additional measures must be taken to ensure proper grounding. Firstly, let's delve into the specific requirements outlined by the NEC regarding grounding and bonding. The NEC mandates that an equipment grounding conductor, or EG, be installed in conjunction with flexible metal conduit and liquid-tight flexible metal conduit. This EGC serves as a dedicated grounding path, providing a low impedance connection back to the source. It is crucial to understand that the flexible conduit itself cannot be relied upon as the primary grounding path due to its inherent limitations. Now let's explore the recommended practice of installing fittings with a grounding lug on each end of the flexible conduit and connecting them with an external bonding jumper. This approach offers several advantages in terms of enhancing grounding and reducing the risk of electrical shock. By utilizing grounding lug fittings, you establish a positive electrical connection between the flexible conduit and the grounding system. This connection ensures a low impedance path for fault currents, allowing them to quickly and safely return to the source. In the event of a ground fault, the fault current will follow the path of least resistance, which, in this case, is the dedicated grounding path provided by the grounding lug fittings and external bonding jumper. This rapid clearing of the fault current minimizes the potential for dangerous voltage rises in the flexible conduit, reducing the risk of electrical shock to personnel. The external bonding jumper serves as a redundant grounding path, providing an additional layer of protection. In the unlikely event that the primary grounding path fails, the bonding jumper will ensure that a continuous grounding connection is maintained. This redundancy is particularly important in critical applications where uninterrupted grounding is essential for safety and reliability. While the installation of grounding lug fittings and an external bonding jumper may involve a slightly higher initial cost, the benefits far outweigh the expense. The added cost is offset by the increased safety and reliability of the installation. By implementing these measures, you are significantly reducing the risk of electrical shock, equipment damage, and other potential hazards. When considering the cost implications, it's important to take a holistic view. The cost of a single electrical accident can be substantial, including medical expenses, lost productivity, and potential legal liabilities. By investing in proper grounding practices, you are proactively mitigating these risks and protecting your organization from financial losses. Furthermore, The generator output conduits often carry high currents, making proper grounding even more critical. High currents can exacerbate the effects of ground faults, leading to more severe consequences. By ensuring a low resistance connection through the grounding lug fittings, you can limit the voltage rise on the flexible conduit and minimize the potential for electrical shock. The external bonding jumper further enhances safety by providing a redundant grounding path, reducing the risk of a floating ground condition. A floating ground occurs when the grounding system is not properly connected to the earth, resulting in a buildup of static electricity or other unwanted voltages. This condition can pose a significant shock hazard to personnel and can also damage sensitive electronic equipment. By installing an external bonding jumper, you are ensuring that the grounding system is properly grounded, mitigating the risk of a floating ground condition. Based on the NEC requirements and the electrical considerations, it is highly recommended to install grounding lug fittings with an external bonding jumper on each end of the flexible conduit when connecting to a generator set. This practice enhances grounding and increases the safety and reliability of the installation. Firstly, this ensures compliance with the NEC requirements, which mandates the use of an equipment grounding conductor in conjunction with flexible metal conduit and liquid-tight flexible metal conduits. Secondly, this provides a low impedance path for fault currents, minimizing the risk of electrical shock and equipment damage. Thirdly, this enhances the overall reliability of the grounding system, reducing the potential for a floating ground condition. In conclusion, when connecting conduits to a generator set, it is essential to prioritize safety and reliability. By implementing the recommended practice of installing grounding lug fittings with an external bonding jumper on each end of the flexible conduit, you can significantly enhance grounding and reduce the risk of electrical hazards. This proactive approach not only protects personnel and equipment but also ensures compliance with the NEC requirements, demonstrating a commitment to electrical safety best practices. Let's delve into the technical specifics of grounding conductors and bonding jumpers to fully appreciate their function and application in generator installations. Grounding conductors, as their name implies, provide a direct path to ground, typically connected to a grounding electrode such as a ground rod or grounding grit. These conductors are designed to carry fault currents back to the source, allowing overcurrent protective devices, like circuit breakers or fuses, to quickly trip and interrupt the flow of electricity. The size and type of grounding conductor are dictated by the NEC, specifically Table 250.122, which correlates the size of the overcurrent protection device to the minimum size of the grounding conductor. It is important to note that the grounding conductor must be installed in the same raceway or cable as the circuit conductors to ensure a low impedance path for fault currents. Bonding jumpers, on the other hand, are used to connect metallic parts of the electrical system together, ensuring electrical continuity and minimizing voltage differences. These jumpers are typically installed across conduit joints, around flexible connections, and between different pieces of equipment. The purpose of bonding jumpers is to create an electrically continuous path, preventing the buildup of static electricity and providing a low impedance path for fault currents to flow back to the source. The NEC provides specific guidelines for the size and installation of bonding jumpers, which can be found in Article 250 of the NEC. When selecting grounding lug fittings, it is important to choose fittings that are specifically designed for grounding purposes. These fittings typically have a larger surface area and are made of corrosion-resistant materials, such as copper or aluminum. The grounding lug should be securely attached to the conduit using a suitable connector, such as a set screw or compression fitting. The external bonding jumper should be made of a flexible conductor, such as braided copper or stranded wire. The size of the bonding jumper should be at least the same size as the equipment grounding conductor, as determined by NEC Table 250.122. The bonding jumper should be securely connected to the grounding lugs using appropriate connectors, ensuring a tight and reliable connection. When installing grounding lug fittings and external bonding jumpers, it is important to follow the manufacturer's instructions and the requirements of the NEC. Proper installation is crucial for ensuring the effectiveness of the grounding system and preventing electrical hazards. Here are some additional considerations for grounding generator installations. Firstly, ensure that the generator is properly grounded to a grounding electrode system, such as a ground rod or grounding grid. This provides a direct path to ground for fault currents and helps to stabilize the voltage of the electrical system. Secondly, install a separate equipment grounding conductor from the generator to the transfer switch or distribution panel. This ensures a dedicated grounding path for the generator and prevents ground loops, which can cause unwanted currents to flow through the grounding system. Thirdly, bond all metallic parts of the generator, including the frame, enclosure, and conduit, together using bonding jumpers. This ensures electrical continuity and minimizes voltage differences between different parts of the generator. Fourthly, inspect the grounding system regularly to ensure that all connections are tight and corrosion-free. Grounding connections can loosen over time due to vibration or environmental factors, so regular inspections are essential for maintaining the integrity of the grounding system. Fifthly, use a ground resistance tester to verify the effectiveness of the grounding system. A ground resistance tester measures the resistance of the grounding path, providing an indication of the quality of the grounding connection. A low ground resistance reading indicates a good grounding connection, while a high reading indicates a potential problem with the grounding system. Understanding the role of equipment grounding conductors and bonding jumpers is crucial in ensuring electrical safety and compliance with the National Electrical Code. These components work together to provide a low impedance path for fault currents, minimizing the risk of electrical shock and equipment damage. In generator installations, where high currents and potential voltage fluctuations are common, proper grounding practices are especially important. By following the recommendations outlined in this discussion, you can enhance grounding and increase the safety and reliability of your generator installations. Let's now explore the implications of different generator voltage configurations on grounding requirements. The generator set voltage mentioned could be 120/240 volts, one phase, 4-wire, 120/208 volts, 3-phase, 4-wire, or 277/480 volts, 3-phase, 4-wire. Each of these configurations has unique grounding considerations that must be addressed. For a 120/240 volts, one-phase, 4-wire system, the neutral conductor is typically grounded at the source, providing a reference point for the voltage. The equipment grounding conductor is then connected to the neutral at the service entrance, ensuring a low impedance path for fault currents. In this configuration, it is important to ensure that the neutral and grounding conductors are properly sized and installed to handle the expected fault currents. For a 120/208 volts, 3-phase, 4-wire system, the neutral conductor is also grounded at the source. However, in this case, the neutral is typically derived from a Y-connected transformer. The equipment grounding conductor is connected to the neutral at the service entrance, providing a low impedance path for fault currents. In this configuration, it is important to ensure that the neutral conductor is properly sized to handle the unbalanced load currents that may be present in a 3-phase system. For a 277/480 volts, 3-phase, 4-wire system, the grounding requirements are similar to those of a 120/208 volt system. However, due to the higher voltage levels, it is even more critical to ensure that the grounding system is properly designed and installed. In this configuration, it is important to use appropriately rated grounding conductors and connectors to handle the high fault currents that may be present. In all of these voltage configurations, it is essential to follow the specific grounding requirements outlined in the National Electrical Code. The NEC provides detailed guidelines for the sizing, installation, and connection of grounding conductors and bonding jumpers. By adhering to these guidelines, you can ensure that your generator installation is properly grounded and protected from electrical hazards. Now, let's address the specific question of whether it is worth the additional cost to install fittings with a grounding lug on each end of the flexible conduit and then install an external bonding jumper around the flexible conduit. As discussed earlier, the flexible conduit itself is not recognized by the NEC as a suitable grounding path. Therefore, the use of grounding lug fittings and an external bonding jumper is essential for ensuring proper grounding. While this may involve a slightly higher initial cost, the benefits far outweigh the expense. The added cost is offset by the increased safety and reliability of the installation. By implementing these measures, you are significantly reducing the risk of electrical shock, equipment damage, and other potential hazards. In addition, the use of grounding lug fittings and an external bonding jumper can help to improve the overall performance of the generator system. A properly grounded system is less susceptible to voltage fluctuations and other electrical disturbances which can lead to equipment malfunction or failure. Therefore, the investment in proper grounding practices is not only a matter of safety but also a matter of ensuring the long-term reliability of the generator system. In summary, the additional cost of installing fittings with a grounding lug on each end of the flexible conduit and then installing an external bonding jumper around the flexible conduit is well worth the investment. This practice enhances grounding, increases safety, and improves the overall reliability of the generator system. It is important to remember that electrical safety should always be a top priority. By following the recommendations outlined in this discussion and adhering to the requirements of the National Electrical Code, you can ensure that your generator installation is properly grounded and protected from electrical hazards. And remember, when it comes to electrical safety, there is no substitute for knowledge and experience. If you are unsure about any aspect of grounding, it is always best to consult with a qualified electrician or electrical engineer.